So the very last lecture is John's fifth. Over to you. Thank you.
Okay, so let me first, as the last speaker, it's my good fortune to be able to ask you all to thank the organizers of this winter school, and also for the HIM Institute for giving us such a great place to have these. Okay, so let's get started with the last lecture in my series. So first off, I want to say I lied to you last time, but thankfully it was an inconsequential lie. My statement of the result of Bainbridge-Smiley-Weiss, you need to add in the condition that it's not uniquely ergodic. It's possible to have, there's very special surfaces that have different orbit closures, but these cannot be minimal and not uniquely ergodic. So, okay, that's that case. It sort of doesn't affect anything I said, but it was incorrect as I stated it. And today I want to talk a little bit about this theorem before I begin asking you guys questions, which is joint with Barak Weiss and John Smiley. And so we've got this funky object here, where you look at all of the surfaces, am I in the wrong place? All of the translation surface in my locus E, which don't have a horizontal saddle connection, which means that there's no line connecting the two cone points of the metric that's horizontal, okay? And over these, you tremor them for time between L and R, okay? And then you take the closure of this, and the claim is that this is a Horocycle orbit closure, meaning there's some very special point, which of course depends on R, so that if you do the Horocycle flow applied to this and you look at everything you see and you take its closure, that gives you this object. Okay? Any questions on the statement so far?
What's the letter that you get out this thing?
S.
It's A? What is it?
It's S. It should be a math cal S. All right. So now, the Hausdorff dimension of this object is between 5/2 and 6 and is strictly less than 6. So in particular, it's a fractional Hausdorff dimensional set. And moreover, these sets are properly nested. So you have a one-parameter family of properly nested orbit closures. Okay? So I think, since I want to ask you guys a bunch of questions, I'm going to restrict myself to outlining the proof that it's actually a orbit closure. Okay? So let me say just a little bit that this is a funny set. So it's the same set if I remove the union here and just write R. Okay? It's still the same set if I put a minus R here and I keep the union. Okay? And if I put a minus A and a B here, it's just the max, you could get the same thing as the maximum of A and B. So it's kind of a funny set. Okay? Moreover, you could consider S sub R. S sub R minus the union over L less than R of S sub L. And this set is G delta, and is a dense G delta, is a residual set, a big set for the bare category theorem in S sub R. This is some kind of a weird family of sets. Okay, that's just what I wanted to say. Any questions on that? Okay, so let's get started with the proof.
Maybe a question, can you draw the simplest example of such a set just in R2? That's parameterized, but parameterization here has the same.
Hausdorff dimension you want me to draw?
No.
Yeah. So a line segment has the property that, like, as you move further, it's nested, so I can get nesting. But when you're doing that with Hausdorff dimension, and then the extreme, I think that goes beyond anybody's drawing skills, and my drawing skills are very bad.
Yeah, probably.
So, I mean, it's a very fuzzy set. That should be what you're saying, that you think, and that there's different pieces that are different kind of ridges that are sticking out at different points. And they're all of different sizes, and they accumulate on each other in complicated ways. So points down the spire, down somewhere along the ridge. So imagine we're keeping this union in, and we're working our way up a ridge. But points in the middle of the ridge also have other ridges that are arbitrarily close to them, and the extreme points of that ridge are arbitrarily close to them.
Ridge is a tremor orbit?
The ridge will be a tremor orbit of a Horocycle segment. Right, because it commutes with the Horocycle's flow, so you should think that these things come in ridges, right? Because if my tremor is sticking up for M, for a little bit of Horocycle flow of M, it's also going to be sticking up. So you get these ridges. And does that make sense to people? I don't know how to draw that picture, but did that somehow help answer your question?
Yes. So, yeah.
Okay, so I want to now tell you a sufficient condition. So what's the goal? So last lecture, where I think I lost some people by using the portmanteau theorem and the bare category theorem, what was the idea of last lecture? I described something more or less explicitly that had a very controlled behavior I liked. And then I changed so in particular we're generic for the E, for this funky space E. And then what I did is I changed the rules of the game, and I changed the word quasi-generic to generic, and I observed that this property was a G-delta property, and I invoked the bare category theorem, and then I produced an even weirder property on a set I have no idea about at all. So basically there's a set I more or less understand, and by continuity arguments, I get related properties for a set I have no clue about. Okay, and that was the strategy of showing that there was a non-empty set, and in particular a residual set of surfaces in the stratum H11 that don't equidistribute for any measure. By going from equidistributing from the measure on the eigenform locus to along a subsequence equidistributing for E, to going to on a subsequence equidistributing for E, I now started talking about a non-explicit set, the explicit set I had before, but it was non-empty, and its intersection with the things that equidistributed along a subsequence for the Lebesgue measure on the whole space, then this intersection would be non-empty. Is everybody okay with that? I'm going to follow that strategy again, and I will have a more or less explicit set of points due to an old theorem of Hedlund that will have a property I understand. And then by continuity arguments, I'll produce a point, and by produce I mean show there exists a point that has a related but slightly different property. So that's the strategy. Is everybody okay with that? So now let me sum the strategy as a proposition. This is a proposition. And what does the proposition say? That for every epsilon, so I'm going to state this proposition so that it's correct, because I have no time to correct my lies. No future lectures to correct my lies, but some of it's technical, and I'll just put it in red, and then I'll ignore everything that's going on in red. Is everybody okay with that? And compact SA and K contained in H11 compact. There exists a Horocycle orbit closure D sub epsilon contained in S sub R, so that D sub epsilon is epsilon dense in S sub R. intersect K. In particular, there exists X in D sub epsilon, so that D sub epsilon is equal to the closure of H of F, sorry, US X. All right, that's what I mean by it's a D sub epsilon is a Horocycle orbit closure. Okay, are there any questions on the statement of this? I'm going to ignore the issues of of choosing a compact subset from here on out. The metric, okay, if everybody's okay with it, and we'll just ignore what's in red. Okay, so I want to tell you what this set is, so I can go over to my notation setting, and I want to let F sub H be equal to the set of all M and E, so that M has a horizontal slit of length exactly H. Is everybody okay with what this is? So you can imagine I give you a torus. You then take another torus, and let's say H is equal to 1. You pick a point in your torus, you flow for time 1 in the horizontal direction on that, and then you glue this to the identical tori along that trajectory. Is everybody okay with that? Okay. Now, because tori are homogeneous spaces, this doesn't depend on the choice of point you chose. I'm okay with this. Okay. And so what's my set going to be? So the set D sub epsilons will be the tremor for time, the union over M in F of H of the tremor for time about M with respect to nu for time. Okay. So what I do is I take this nice set F sub H. It's going to have two different ergodic measures for each surface on it. It's going to have two different ergodic measures that are exchanged by my involution that exchanges the two tori. Okay? I pick one of those ergodic measures, and I tremor with respect to that for time r. Okay? So let me just first mention that when I was defining this, I was using the set E min, right? And I'm now probing it by these set D epsilons that are not, in principle, even in it if I forgot that I took an orbit closure. But the point is these are going to fall into the set in the orbit closure. Is everybody okay with that? And let me just stress that when we talked about tremors beforehand, we had a rather concrete example. The tremors in this case are exactly the concrete example, right? There's some, you can write these objects as very, very long and thin tori, glued along a particular horizontal slit of size h, and then you can move one of the two tori and leave the other one unchanged. And that's the picture of what's happening. Is everybody okay with that? So this is the simplest situation for the tremor. And if you somehow got confused of when I was taking limits or tremors or whatnot, that's not what we're doing here. We're just doing the simplest case. In an abusive notation, I'm going to denote this set as trem R of F sub H. That's what it's going to be. Hopefully people are more or less okay with that notation. Okay.
Why is this an abuse of notation? Because you didn't choose the...
I've never set up this notation, what it means to trim our set. So, yeah. I mean, one can imagine setting up notation to do this. I didn't do it. Okay. All right. So, so what's the idea of the proof of the proposition? So idea of proof.
What are assumptions on mu for the d epsilon? Because like on the other side we had mu as ergodic with respect to the horizontal flow. Like when you're taking this mu d epsilon, what is mu?
Mu is one of the measures on the tori. Right here you have a super concrete measure on this torus. Right, because you split into two tori, you're taking just... All right, so what's the idea of the proof? The idea of the proof is as follows. S sub L is a compact metric. S sub L is a complete metric space. For all epsilon greater than 0. There exists an L, so that U sub epsilon equal to the set of all M in S sub L, S sub R, M in S sub R, so that the union of S, absolute value of S less than or equal to L of HSM is at least epsilon dense in E. Notice I am now doing what I said I would be doing, which is ignoring the issues of compact sets. This is not true, but we're just ignoring compact sets. You introduce the compact set, and then it is true. Okay? And open. Okay, let's talk about why this is true. So 2 is, so the fact is open and non-empty. By definition, this set is open. Is, sorry, at least should be more than. Denser than 2 epsilon is denser than epsilon dense. I basically tried to use English to phrase this as an open condition. The fact that it's not empty is by the statement of the proposition. Okay. Everyone okay with this? Okay? Moreover, it is epsilon dense. If L is large enough. Okay, so playing around with the existence of this d epsilon for smaller and smaller epsilon, you could show that if you fix an epsilon, you can pick a smaller delta, so that the orbit that gives you this denseness for d sub delta has to actually have a long segment of its orbit also have this property, and there you're able to obtain this result. Everybody okay with this? All right, and then 3, Baire category theorem gives us the theorem. Baire category theorem. Gives existence of M tilde. So let's recall what the Baire category theorem says. The bare category theorem says that the intersection of open and dense sets, the countable intersection of open dense sets, is non-empty and in fact dense. Okay? So what do I want to do to invoke this? Let V V sub n be equal to the union from I equals n to infinity of u sub 1 over I, okay, is open and dense. So by the bare category theorem, the intersection of the V sub n is non-empty. But the intersection of non-empty, of this non-empty, but the intersection of the V sub n's is, has that its Horocycle orbit is 1 over I dense for all I. Is everybody okay with that? If M is in the intersection of the V sub n, its orbit is 1 over n dense, its US orbit is 1 over n dense for all n. And in fact, it's dense. Everybody happy about this? Okay. So now let's try and explain how we prove that this set exists. Okay. So finding d epsilon, showing there exists H, so that trim R is d epsilon, can be. Okay, that's our next step. Everybody happy about this? So let's talk a little bit about what f sub h is. F sub h is basically the space of tori. I have stipulated a condition that gives it on surfaces in the space of two tori glued along a slit that identifies what the slit is. So that the only thing you're left with is the space of tori. You're allowed to perturb in the space of tori. Okay? So there's a theorem due to Hedlund. Actually, this is probably older than this. So let's just theorem question mark. Maybe Alex can tell me who this is due to. There exists a US dense orbit in SL2R on SL2Z. And thus, so corollary, there exists a US dense orbit in f of h. Hedlund, or would this be even older? Okay, so this is old. I mean, it goes back at least to the 30s. Okay. All right. So d sub epsilon needed two things. It needed to be pretty dense in my space S sub r, but it also needed to have a Horocycle orbit that was dense in itself. And Hedlund lets us do that at least on the level of f sub h. Now on this locus, the tremor is continuous. So on f sub h, the tremor is continuous.
So the tremor is an action on f sub h?
Yeah.
Or do you actually, or is it a 2-to-1 bundle above F?
Yeah, so hiding in the background is the fact that it's not a 2-to-1 bundle. It's a well-defined action. It doesn't matter which measure you choose.
So if Fh is SL2R mod SL2Z, is this action writable in terms of, so what kind of, I don't know anything that acts on SL2R mod SL2Z rather than elements of SL2R.
No, this is, we're in an ambient space.
But you're,
Imagine you put SL2R, mod
so
SL2Z,
yeah,
and R to the
takes you
ninth.
out.
Yeah.
Okay.
Which is more or less the
Yeah.
situation we're in. It's all what's going on in the ambient space that you put it in. But you bring up an interesting point. This is a fun interplay where there's a situation we know a lot about. We're putting it in a space we knew less about. We're trying to take advantage of what we know as much as we can. So now because the action of this on that is continuous, we get the next corollary, which is there exists a US dense orbit in trem R of X of H. Okay. Is everybody happy with this so far? Okay. So now all I need to do is to prove that trem R, that for all, so now we have the following proposition, which is once again a lie, but since I'm writing the word proposition, I don't want to lie, so I'm going to write some things in colored chalk, which is for all epsilon greater than 0, and K contained in each 1, compact, there exists H naught, so that trem R of F of H is epsilon dense in S sub R intersect K for all H bigger than or equal to H sub 0. Okay. Is everybody happy with this? Now I would like to ask you guys some questions, some open possible research questions. So I'm just going to in words say what's going on with trying to prove a statement like this proposition, which is enough to complete the proof of the fact that we've built a weird orbit closure. Okay? So what's going on in this statement? So I have a measure that I put on one of the two tori that are invariant under the horizontal flow that's in my set F sub H, because there's a horizontal separating curve for my GS2 surface that separates it into two tori. Okay? It turns out it doesn't matter which torus you put the measure on, so you pick one of these and you put the measure on it. What you want to show is that this measure on this torus that in this way of putting measure on this torus, that where the flow is not going to be minimal, and you can actually identify where it sits, which is on one of these tori that's separated by this slit. You want to show that if I take anything that we could build by our construction beforehand, so you have something that's possibly minimal with two identically glued tori along a slit that has a non-uniquely ergodic horizontal flow that's possibly minimal, that you can find a nearby torus to it, which when you do this gluing along a slit, the measure is nearby to the ergodic measure on that torus. This is actually very simple to do. You take the way we constructed this in lecture 2 as an infinite sum, you truncate the infinite sum. That's a great way to do this. Okay? Now, you really want to get this for all large H, because you want to simultaneously approximate lots of different measures. Okay, this you can do by finding it on a periodic guy. You change your direction a little bit, and you build a periodic guy where you can do the same argument. And then from the periodic guys, you can build for many h's in many nearby directions, you can achieve the same result for them. Okay? That's still not good enough, because what that does, I talked about these ridges when Martin asked the question. These ridges that you can think of are funny S sub r orbit, as having these ridges sticking up. All I've argued now is that the r tremor of f sub h is close to the top of the ridges. I want it to be close to middle points on the ridges. But the periodic guys are very well built for doing this. By changing your slit a little bit and your periodic direction a little bit, you can actually find a nearby surface to this periodic guy where you're approximating the midpoint of the ridge. Indeed, if you think in terms of continued fraction expansion, imagine I have an enormously long continued fraction expansion that represents a periodic object. So at some point it's actually a rational number, but it's described by an extremely long word in continued fraction expansion. And then after that, I pick an enormous number to be in the next column, and I choose my slit to be half of that. Half of that number. Okay? That's going to give me a point that's close to the barycenter. And by playing along with this collection of arguments, you can prove the proposition. Okay? All right. Are there any questions on this?
So where did we use this proposition in the proof of the?
Yeah. So we now want to run the argument set up by this proposition, right? We're just proving that there's a U.S. orbit closure. So I needed a couple of things. I needed a set that was pretty dense in S sub r, and I needed that set to itself be an orbit closure. Headland, or whoever it's due to, gives me that it's an orbit closure essentially free of charge. But I need to get the density of it, okay, in this space before you take the closure. Okay? And by truncating the sum, and another trick, you can get the top of the ridge. But then you want to fill in the points along the ridge, and there you want to play around with your slit a little bit more. And did that answer your question?
Yeah.
Any other questions? Great, now it's my turn to ask you guys questions. All right, so let's start off with a question. What is the Hausdorff dimension of S sub r? Okay, and I have a guess. Schematically, you can think of S sub r as being taking E and having, there's a set in E of Hausdorff dimension 4.5 and adding line segments at each of the points in this set of Hausdorff dimension 4.5. 4.5 plus 1 is 5.5. Proof, right? No, because these line segments can vary. Their height varies. Okay, that's not all that problematic to get a lower bound, but their direction varies. If you think for a little bit, you can kind of convince yourself that if you have a set of positive Hausdorff dimension and you start sticking line segments out of it, if you let your directions vary wildly, you might be able to pick up more than Hausdorff dimension 1. Okay.
With the line segments themselves or after taking a closure?
No, just with the line segments themselves. You can kind of convince yourself of this. Okay, another remark here is that you more or less don't need to take a closure. Right? We're describing something that's going on in E min. You can think of E min, the complement of E min, being the things that have tori, which have uniquely ergodic horizontal flow, but lie in one of the f sub h's for some h. And those we kind of understand even better than anything else. Those are the objects we understand the best, and their tremors are all contained in R, S sub R. Their R less than or equal to R tremors are all contained in S sub R. But then there's the periodic guys, and I haven't even defined for you guys the periodic guy, what a tremor with respect to for a periodic guy is, but those can be understood. S sub R can be more or less completely understood, and it's completely, basically all tremors for times strictly between 0 and R, and you eat up all of those. Did that answer your question?
I think so.
The closure is a very mild thing. Okay, so what is that? So that's the guess? Now, there's the next question. If M is in E and F sub M of T is minimal, let's say, and has no horizontal saddle connection, is US of M, is its Horocycle orbit closure equal to, I'm sorry, U sub S of trem of M, comma, nu sub R equal to S sub R. And nu A or E. A F measure. Okay. Sorry, F to the T of M. Okay. So let me talk through this. So if I have a surface and the locus, my locus E, and it doesn't have a horizontal saddle connection, so that means its horizontal flow is minimal, possibly uniquely ergodic, possibly not uniquely ergodic. And I take the time R tremor with respect to one of its ergodic measures. There's two possibilities. One is I don't leave my locus E. I was uniquely ergodic. My measure is Lebesgue measure. I'm just doing tremor with respect to Lebesgue measure, which is Horocycle flow, great. In that case, I'll get E. And in any other case, I'll get something different than E, and my question is this S sub R? I think this question is really great at showcasing that I sort of have no clue what's going on here, right? I do these arguments where I think about very special circumstances. I prove some kind of results in it, and then I use continuity arguments and quote the bare category theorem to build weird objects. But I actually sort of don't know what's going on. I can do one or two little things, and I just try and stack these on top of each other and repeat them over and over again, but I don't really know what's happening, right? And this is, I think, a really good way of pointing this out. So I don't know what the orbit closures of tremors are of most of these surfaces. I have no idea.
Did you take their, so R is fixed or R is between 0 and some R node, or
Ask it for R equals 1/2 or ask it for all R. I think you get the same answer. I think if there's an exception for R equals to 1/2, there's probably an exception for all R greater than 0.
My question is, when you defined SR, it was defined in terms of
a union.
a union, right?
Yeah,
Up to time R.
up to time.
And on the left-hand side, you didn't specify you took closure, right? But you didn't specify the parameters. S runs through R, through the reals, right?
Oh, I see.
On the left-hand
S in the
side.
reals.
And R is
Have I
fixed.
answered your question? R is fixed.
On the left-hand side, R is fixed.
On both sides. R is not changing.
But on
This
the
R is
right-hand
the same as
side,
this R.
let me clarify my question. On the right-hand side, S sub R is defined as a union
Correct.
of tremors
Yeah.
where the parameter runs up to R.
Correct.
On the left-hand side is a fixed R.
Correct. And there's the
And
same
you're
R.
claiming that you're claiming that the Horocycle flow of a tremor or of a fixed R accumulates on tremors of lower R's.
Yes, that's
It's
this.
part of the claim.
Yeah. No, the fact that there is an orbit that has that is basically hiding in here, and which I was talking through with these periodic objects. What I was trying to get at with this choosing the nearby periodic object, and then choosing the next term in the continued fraction to be enormous, and choosing the slit to be of half the length, and getting something that's a convex combination. That's how you get this union here. That at first should seem surprising. Did that answer your question?
I think so.
Okay, so I like this question. Okay, so,
There's a question in the audience.
oh, thank you.
Sorry. Maybe there's something that I'm missing, but regarding your first question, why are we expecting the Hausdorff dimension to be constant as a function of R?
Yeah, that's a good question.
Okay.
Because I expect 5/2 to be a constant.
Okay.
That would be good. Right, in some sense, the extreme points are big compared to the non-extreme points. Going back to Yuri's point, you know, there's this union over L's less than or equal to R. But there's this point here that I just said in words, that this set is G delta. So you could think of the extreme points as being big compared to the points before them. So maybe it's an increasing function, I don't know. Now, I don't think it is, because I think 5/2 is a constant, but yeah. 5/2 is a constant, but I think we know what the number is, so. And I'm sorry, I think the number is a well-defined number independent of R. That's why I think it's true. But that's just what I think, I could be wrong. Okay, now the next question is, you'll notice I chose the letter E for this. And I had something about tori, I had something about slits, I had something about gluing, and I chose the letter E. It seems a little bit weird, right? So this example of this orbit closure falls in a countable family of SL2R orbit closures called eigenform loci. And so the natural question is, do this for other eigenform loci. And let me make a statement. Hopefully the paper where we do our work will come out on the archive soon. And the methods that are presented there are fairly different than the methods I presented here, especially in the treatment of non-uniquely ergodics and in the words I blathered for this proposition here. I chose to say arguments that I am more optimistic of will generalize to other eigenform loci. Okay? So our paper uses a lot of tricks that take advantage of the fact that we're in a space, we're in such a nice space that has an involution and has two tori glued along a slit. But I think that the ideas behind them are much more flexible than that and have a good chance of working more generally. But then there's some things where I think new work will be needed. Yes.
Can you say the first place where this breaks down, since I think you said Bainbridge, Smiley, Weiss holds for other eigenform loci?
Yeah, so it all comes down to, so this proposition is still true if you picked a different eigenform locus. Okay? It boils down to finding these, and I suspect it's not actually that hard. You can almost imagine what you would call f sub h. Now, maybe it's not connected anymore, so you need to pick a connected component. And it won't be hard using Bainbridge, Smiley, Weiss, again, to show that that's an orbit closure. But then showing that the tremor of that is dense, that's what all the work is going to be. Picking a connected component of whatever the variant of f sub h is, and proving that the tremor of that is dense. Did that answer your question? Okay. All right, we've got more questions. Here's a question I really love, which is, does there exist M so that M is not in the omega limit set? Of under US. Okay. So, what do I mean by this? I mean, there exists an epsilon greater than 0 and S naught, so that US of M is not in the ball placed about M of radius epsilon for all S bigger than S naught. Okay, so this is topological recurrence. So the Horocycle orbit is, some people say it's recurrent because there's a compact set it always will recur to. And then the question I have is, will it recur topologically? Will it recur to itself? I don't know. My understanding is the fact that in the homogeneous setting, at least in general, the way that people can prove that there is no such exception to the Horocycle, to a unipotent flow for this property, is by understanding the orbit closures. And there's no easier way, but maybe the experts in the audience can correct me on that. Yeah, so, but we have weird orbit closures here, so I mean, that strategy seems, well, I don't want to say hopeless, but it seems less promising. So the question is, does that mean there's an exception? Which would, I guess, be maybe some kind of evidence that this is not just a coincidence in that, okay, in any case.
Potentially one of your examples is such, or is it not the case?
Yes. I'm not sure I would believe that you could do it with a torus glued on a slit. That might be just too little freedom. But as more evidence of just how ignorant we are, I don't know if there's a tremor of a surface in E that itself isn't recurrent to itself. That's not topologically recurrent. So just as you said, I don't know if we already have the place to look. I'd be a little surprised, but...
But in terms, let's say in terms of measure, you did prove that, right?
So everything we're talking about is zero sets, right?
No, but in terms of accumulate, like the genericity, you start from a point and you showed us that in terms of limiting measure, the limiting measure lives far away.
Yeah. So in particular, if I understand what Uri is saying, that if I fix any epsilon, so in homogeneous setting, if I fix any epsilon greater than 0 and I look at any point, the Horocycle orbit will deposit definite weight to that neighborhood, where the definite weight depends on epsilon. In our example, you pick a tremor of a point, you pick a neighborhood about it that does not intersect E, such a thing exists, you'll deposit 0. So measured theoretically, these things are not recurrent in the topological sense. Did that answer your question? Okay. All right, we can keep going. Does anybody else have other questions on these? Great. Okay, I'll keep going. So our arguments, and hiding in this statement of this question / task of do this for other eigenform loci, is my statement that sort of our arguments, some of them take advantage of the fact that we're a cover of the torus. Okay? Now, there's some eigenform loci where you don't arise for cover of the torus. Excuse me. And there, that won't be accessible to you. Excuse me. But still, the eigenform loci can be described as two possibly different tori, but with special relations glued along a slit. In this kind of construction where you've got this piece in SO2R, and then there's just this one additional piece of the slit that you're choosing, is very helpful. And I suspect it's going to be very helpful. And if you move yourself away from this setting, I suspect it's going to be more challenging. And there's places where there's bigger orbit closures where you can't just worry about one direction that's kind of your group direction and then moving around one slit or several slits. And these have been discovered by Kurt McMullen, Ronan Mukamel, and Alex Wright. And Alex Eskin, Kurt McMullen, Ronan Mukamel, and Alex Wright. And so then the question is, can you run this construction here? So that's the next question. Question, do there exist translation surfaces in the new orbit closures? Mukamel. And right. And then the same group of authors with Alex Eskin. So the first one was the last 3 authors, and then there was, I don't know, 6 other ones found by the collection of the 4 authors. I hope I'm getting the numerology correct on that. Do there exist M in these so that it has a non-uniquely ergodic horizontal flow? Is minimal and not uniquely ergodic. Okay. Now, here's a further question. Is there such a surface, such an M, with ergodic measure nu? Ergodic measure nu. So that the trem of M with respect to nu, say for time 1, it doesn't matter how long you choose, is not in the locus. And now the last part of this question is more suggestive, which is what can you do with this? So it would be surprising to me if somehow the fact that our orbit closures we're dealing with are very restricted. They're in lingo SL2R plus rel or rank 1. Somehow restricts our level of freedom. I wouldn't be that surprised by this. And maybe when you leave this setting, you have more options. Now this is very speculative, so I can't say anything more than that, but I think in any case, the first 2 questions are kind of interesting in their own right, and at least, and the second question has a formulation that's not very hard to come up with for the experts, which can be phrased in a tremor-independent way. And I think these are interesting questions independent of tremors. Right. Any questions on that question? Okay. So there's, in the more topological side, there's something called the earthquake flow. And the Horocycle flow and earthquake flow are closely related. In fact, they're measure conjugate in the principal stratum. And so the question is, can you build weird Horocycle orbit closures? I'm sorry, earthquake flow orbit closures. Can you build weird earthquake flow orbit closures? Failure of generosity. And because this is just a measurable conjugacy, not a topological conjugacy, I don't think anything is immediate. All right. Now let's talk about another question. So in the subject that I'm in, fractional dimensions show up sometime, but it seems that essentially all of the times they show up, it's a half integer. And I even suspect that this is a half integer. But I suspect that for kind of very special reasons. For the experts, but the fact that you're not uniquely ergodic basically means you have 2 Lyapunov exponents of 1. And you can make this precise by talking about singular values. Now, because you're symplectic, that means you have 2 of -1. Now, other than that, you have your rel direction, which gives you another 0. That's very well controlled and very well understood. And so there's sort of no room to move around. If you think about moving your non-uniquely ergodic guy nearby, in particular, if you sort of belong to the same simplex of rosy induction, whatever this means, you should be moving like you should be moving like the size of your matrix of rosy induction to the -2. So that's part of the reason why I don't think you should be able to pick up any extra Hausdorff dimension from how these lines wiggle. But more generally, you should be able to pick up extra dimensions for how this line wiggles. There should be extra space. The two ergodic measures should not be enough to exhaust all of your Lyapunov exponents other than to exhaust all of your Lyapunov exponents. Okay? And so my idea is then you pick up different Hausdorff dimensions from these other objects, from the wiggling you can do within a simplex of Rosie induction by moving between non-uniquely ergodics there, and pick up a number that's not a half integer. I'm gonna write this as a question. This is maybe more of a question for the experts. So questions. There exists, question mark, a Horocycle orbit closure of irrational or at least not half integer Hausdorff dimension? Does there exist a Horocycle orbit closure of irrational or at least non-half integer Hausdorff dimension? And I think tremors in other situations other than eigenform loci are natural places to try and go about doing this. And now let's do one last question. Is every surface, every translation surface without horizontal saddle connections quasi-generic only for nice measures. Only for nice measures. And I'll wrap it up there. Okay. Okay, so for example, SL2R or SL2R invariant measures. Okay, thanks.
So, questions, comments? Explanation?
What happens to FH when I vary H?
So what you should think about what you're happening is, so you have the following heuristic, that I can fix the surface I started with, that's in E, and it's not in any F sub H's. And I want to know about its long-term dynamical behavior, say up to time T for T large. You should heuristically think that if you choose H close to T, you can find a surface in FH near this surface whose behavior kind of mirrors it, at least up to that time, and then the two halves can no longer interact anymore, and they just now have a separate life from each other. So if you have something uniquely ergodic and you play this game, up to time H, you'll look up to time T, you'll look as uniquely ergodic on this nearby guy in F sub H, but then you don't know what happens. Or then you can't look more uniquely ergodic, things don't get mixed any further. And that's kind of the heuristic picture you should have in mind. So as H gets bigger, you're not just probing your space of tori better, but you're probing how it sits in this E space very well. And as H gets bigger, you're probing it better and better. Did that answer your question at all?
Sort of, but I was referring to you said that FH is basically SL2R with SL2Z, right?
Mm-hmm.
So this has a nice measure on it.
Yeah. Oh yeah, you can push that measure down.
As H goes to infinity, this measure goes to...
Oh, it goes to this mu sub E, this Lebesgue probability measure on E. That's like this. But I think that more is true. It's doing it kind of in a dynamically meaningful way, where you can kind of relate what's going on.
Any other questions or comments? So, I'm sure we want to thank the Hausdorff Institute and the fantastic speakers we've had for the update today. It's been a great week. And thanks to all the participants for your contribution also.